Hello, hello. Welcome, everyone. So this talk is about lean consensus, spec and implementation, and I'm Gajinder Singh. I run Zeam. So we'll look again a little bit of pilling process, right? We'll do some pilling while lean. We'll then look at the work that we have done so far. Then we'll take a deeper dive into the components that make up lean, and then we'll look at 2026 plan. Again, a bit of shilling. We are a global team running out of India, and we are on a mission, and the mission is lean Ethereum, and we are fighting on all cylinders. So now looking at the straw map and coming to the topic. So if you look at L star hard fork, this is where we want to get to post-quantum security. We have post-quantum attestations, we have lean VM aggregation, we want to reset some tech debt, and we want to start introducing endgame finality over here. But that doesn't stop over here. Then after that, we want to do one slot finality, and we want to go to 1 million attestations per slot. And then we also want to take the post-quantum work benefits to the other layers, data layer and the execution layer, even though execution layer is a bit tangent to lean Ethereum, but things basically tie up. But things also start quite early because we will have post-quantum pub key registry very soon, and then we will also have post-quantum heartbeat that will help us in finality and consensus. So now coming to lean Ethereum. So it is Ethereum on ZK rails. And as we know, we have 3 layers. We have consensus, data execution, and what we want is post-quantum security. We want verifiability, that anyone in the world with a very low-powered mobile device can verify the chain. And we want censorship resistance. And that's the base setting. Now, what do we want to do on top? We want to be internet's settlement layer. So for that, we need 10K transactions per second on the execution layer itself. And we want 10 million transactions per second in the entire L2 ecosystem. So that basically corresponds to 1 gigagas per second on execution layer and 1 teragas per sec on the L2 on the data layer. And we want faster finality and inclusion. And on the consensus layer, we want 1 million attestations per slot. And all the benefits that we basically get for post-quantum security on the consensus layer, we want to take it through other layers. And this is sort of a value proposition diff between the current chain and the lean chain. So we basically want post-quantum, again, rehashing what we already talked about, fast finality, censorship resistance. We want to reduce the node complexity. We want to make protocol simpler. This is trust and verifiable complexity, which we want low, not just trust/verifiability. Trust/verifiable complexity is low. That means that the trust and verifiability should be high. And we also want decentralized block building. I mean, even today, theoretically, it is high, but we only have very few builders. And that is a property that, okay, we are saying that we can compromise a bit on it. So coming to lean components. So there are 3 pillars that make up lean: post-quantum signatures and snarks around them, and fast consensus, and optimizations and improvements on P2P network. And when we are doing all those things, we'll basically, it will affect the entire way the consensus runs. So there will be a tech debt reset. We want to make the protocol simpler. Okay. And coming to what we have done so far. So we have done DevNet 0, which was just a start between 3 clients. It was just a warm-up using 3SF Mini. Then in DevNet 1, post-quantum XMSS signatures came in. We jumped to 5 clients. Then we did SIG aggregation in DevNet 2. At DevNet 3, we introduced aggregator's role. And we have 10 plus clients, but okay, some of those clients are wipe coded AI, but And our spec work for DevNet 4 is complete, basically, which is recursive aggregation across the attestations that are there so that that the block size only has, block size can be really low. So we don't want the attestations which have same data to have different, which are still across the subnets to basically, be packed differently. And in DevNet 5, what we are planning is recursive aggregation across block, which basically means that the block will have just a single signature. There won't be many signatures. For example, even today, if you look at the block, attestations have their own signatures, and then there is a block signature and whatever. If there are other signatures, if there are other objects packed. So now in DevNet 5, we will just move to one single signature for the block. And DevNet 6 and 7 is something that we are yet to decide, but I'll talk about it towards the end. Again, now let's look at post-quantum. So for post-quantum, we have selected XMSS, which is or one-time signature scheme. And what really happens is that you have these one-time keys, and so each of these are one-time keys, and you basically drive a public key. For all of these keys, you basically generate a sequence of these keys till whatever you think is the lifetime of your validator. You get to the leaves of this tree, and then you do a Merkle tree, and basically the root of this Merkle tree is your public key for a validator. And verification and and aggregation of this will happen through Snark. This is hash-based signatures. So BLS keys are more elegant in terms of aggregation and verification, but that is not the case over here. And that is why we will basically do them through LeanVM, something called LeanVM that will talk about that. One important thing to mention is that this signature scheme has been improved by some optimizations, and there is a paper top of the Hypercube if you want to look deeper into it to make sure that we get a very secure post-quantum scheme. And coming to the aggregation part, so LeanVM is the VM that will aggregate these, that is actually aggregating all the signatures. It is Ultra RISC-V that there are only 5 instruction set, 5 instructions in the set, and we are using Poseidon 1. Earlier we were using Poseidon 2, but we shifted it back. And we are basically doing recursive aggregation on top of it. And the aim is to have this LeanVM formally verified. And we don't want to basically say that, okay, if you are doing aggregation, you need GPUs. If you are an aggregator, you need GPUs to run. So CPU is still the target. And we want the final size to be produced so that we can, to be less than 1.5 KB so that, we can just use a single packet to transmit them. And once we do all this for consensus, we take this to data and execution. So looking at consensus, currently we have the consensus on Beacon, which is basically Casper. There is LMD Ghost running, and then there is a finality gadget. But the problem with this is that it is tightly coupled, causing some of the issues and some of the ways we can't reason about edge cases. And it basically runs its own epochs. So if we want to do faster finality, we can't have epochs anymore. So here we basically want a 2-layer fully decoupled consensus protocol. And this image is from Jan's presentation, but attribution will come later. So what is happening is that you want an available protocol, and that basically and then you want to run a finality gadget on top of it. So you want fast available chain and decoupled finality mechanism with substantial stake security. And what about 3SF, what we are currently using? So it has fast confirmation and K-deep confirmation, and it has 67% stake-based finalization mechanism, but it is still coupled with block production, and we want to do one slot finality, so it's not good enough. And here comes the attribution to Jan. And so what we actually want to do is we want an availability protocol called Goldfish, which is basically a heartbeat of randomly selected 512 validators who will basically do this heartbeat, and those are selected every slot. And then we have a finality gadget running on top of it. So Goldfish will be used to select the available chain. And finally, the votes will basically be counted, and the finality gadget will give us finalization. Yep. So this is the explanation of how Goldfish works. And I suggest you look at Jan's presentation for further getting deep down into how consensus is going to evolve. And this is basically the basis for PQ heartbeat that we talked about in the straw map. And it doesn't need aggregation, so we don't really. So we want to eliminate the time between vote and fast confirm. We don't want to add an aggregation layer on top of it, but it's just 512 votes, so that's fine. And then with LMD Ghost and finality gadget, you will have your consensus. Coming to P2P gossip. So let's look at the objects that are there in the lean consensus network. There is attestation and PQ heartbeat. Basically, the objects are similarly sized. So it's basically an XMSS signature, which is 3 kilobyte, but we can decouple it into two halves. You saw the tree. So basically, if we send the signature separately, which is basically the leaf mapping onto So if we basically send message when it's signed, it gets mapped onto these hash chains. And if you basically send that only and you decouple this tree and send it separately, basically you can fit it in a single network packet, which is basically what we want to go for. And all these attestations, they are happening at their logical subnets. And what we want to find is a fastest path to the aggregators. Coming to aggregates, so what aggregators are producing, so which basically are lane VM proof, and they are roughly 3 kilobytes. And we want to again target them to a proof of 1 kilobyte. And it is possible, researchers are working on it. And then we want that they are, so these aggregators, they are at minimum hops to every validator that is out there. And then we want, so then there are blobs, but blobs are already sort of being worked on the beacon layer, and that is something that will piggyback from them. And on the blocks, again, there is a single aggregated proof for everything so that we minimize this signature data. And eventually we want block in blobs. And this aggregated proof is basically 300 KB. When I talk about this aggregated proof, I not only mean the proof of signed attestations or the block signature. I also mean that the proof of the validity of the block, for example, which ZK VMs will verify and produce the proof. So that is why this is 300 KB, because the entire proof will be of this size, which will just validate your block. And which will just not only validate execution, but also the consensus and all the objects in it. So again, the emphasis is trying to get to the single MTU unit, and so that we can use datagrams and Quick. We are already using Quick on the current P2P layer. And should we transition to an app-aware ETH P2P for the reasons that we can pipeline traffic per duties. We can do some source-aware peering so that aggregator can be, very much connected to most of the validators. And we want to remove the next slot bidding. So if you don't know about next slot bidding, what happens is that gossip objects of the previous slot are still being distributed in the current slot. So that is what is next slot bidding. And we want R and LC type encoding for big objects like block and blobs. Eventually, block will also come in blobs, which is the long-term plan. So in the end, everything is blobs. Now coming to our plan, so we basically are at the DevNet 4 testing stage because the spec is done for that, and for DevNet 5, we are basically doing spec, looking at DevNet 6 and 7. We want to do the consensus protocol that we talked about, and we want to start introducing the P2P layer optimizations. And so the 2026 goal is to run 10,000 validators in a long-running DevNet. And the stretch goal is to basically have a public testnet. But that also means that we'll need to integrate deposit and execution integration. So this is sort of a stretch goal. But once we have that, we'll be able to launch a public testnet where people can come in, they can start deposits, they can do deposits, get their validators activated, and just join in the network. Thank you. Questions? Yep, please.
So I'm not 100% sure if you have mentioned it in this presentation, but with current layer 2s of Ethereum, you have like zero knowledge proof protocols, right? And they are all facing the challenge that they have very slow finality. How does lean Ethereum is going to tackle both problems of having zero knowledge proof and fast finality?
You should have come to my yesterday's presentation, which talked about native rollups, so where I just basically discussed the problem over there. So when you talk about L2s, so there are objects going into the L2, and the problem over there is that, for example, there is a block that is produced on L1, then it takes L2 sequencer a bit of time to detect those logs and build a transaction that they commit to the L2. So this layer is still fast, like they take 60 seconds, but the reverse layer is extremely poor because they batch for hours and then they generate batch proof for hours, and then they wait for finality on L1 which might take 10 minutes, 15 minutes, and then they release, for example, the money. And this is for non-optimistic rollups, right? Optimistic rollups will wait for 7 days instead of finality for the fraud-proof window to happen. So if you want synchronously composable rollups, basically you need to go to native rollups, which will happen, I think, around the same time in L-star. Yeah.
Thank you. How do you do the signature aggregation? Is it the same as post-quantum or?
Yes, so basically there is lean VM and a snark, post-quantum snark is generated. So if you want to get into details of lean VM, you can basically go into lean Ethereum GitHub organization on the GitHub, and you will get lean sig, and then you will get lean multisig. Lean multisig is the one that is doing aggregation. So you can look deeply into it and check how it's being done. I mean, it's totally out there.
Hi. I'm wondering if we use native rollup, of course, it will make the confirmation faster and actually give a better security guarantee. But what that also means, like a validator on the Ethereum mainnet need to help to do much more like data availability sampling than before, because now some layer 2 they can use other DA service, right? But after the native rollup, actually all the data will be directly put into the blob, and assume the validator will need to, when they re-execute the layer 2's state transfer, they also need to do the data availability sampling. Will that actually increase the cost?
Data availability sampling is basically when you are posting your block, right? So you are posting your block because you want the data to be available. And that, so when I say block, we are posting your block, you are posting your L2 block, right? So you have created the batch, and you want, when you are basically confirming that batch on L1, you want to spread that data out, that is data availability. At that point, you can still say that, okay, I can use any DA layer, but if you want to finally settle, which is basically providing the proof of your L2 batch execution, right? You can still do it directly through this particular layer, right? You don't need data availability to post your proof. I mean, the proof itself is could be 300 kilobytes, but if you just use call data, you can still do it. And when native rollups will come in, basically what will happen is, again, the proofs will be validated at CL level, and those again might flow as blobs. So all of those things will be optimized as such for native rollups. But if you are not a native rollup, you need to take care of all these things. All right, thank you.